The massive reinforced concrete that built the modern world carries a hidden, devastating flaw deep inside its steel core. Over time, atmospheric carbon dioxide reacts with the concrete matrix, lowering its naturally high pH. Once that protective alkaline barrier drops, moisture penetrates the porous shell and reaches the internal steel rebar. The steel rusts, expanding up to 4 times its original volume, exerting immense internal pressure until the structure shatters from within. Yet, along the Mediterranean coast, the submerged harbors of antiquity tell a completely different story. These breakwaters have absorbed the crushing kinetic energy of the sea for 2 millennia, holding firm against storms, saltwater, and time. Roman engineers achieved this incredible feat without a single ounce of industrial steel. They designed their monumental architecture to exist in pure compression, relying on thick, massive geometries like domes and arches, where gravity continuously pushes the materials together. A modern coastal pier built today is generally expected to require critical repairs or face structural failure within 50 years of its initial curing. The structures of the Roman Empire remain intact after 2000. For centuries, historians and civil engineers assumed these surviving ruins were mere anomalies of survivor bias. The longevity of Roman infrastructure seemed to defy the basic laws of material science. The atomic architecture of these ancient ruins provides the chemical blueprint needed to stabilize our own failing global infrastructure. Roman concrete was forged from the tectonic violence of the Italian peninsula. Builders utilized a highly reactive volcanic ash extracted directly from the restless caldera of Campi Flegrei and the slopes of Mount Vesuvius. Recognizing its unparalleled hydraulic strength, the Roman state transformed this volcanic soil into a strategic resource, deploying vast merchant fleets to ship millions of tons of it up to 1,200 miles across the sea to construct distant marine projects. Working underwater required specialized temporary enclosures. Engineers drove double-walled timber piles into the seabed, sealing the gap with packed clay to create a watertight chamber known as a cofferdam. Inside, enslaved laborers operated continuous banks of Archimedes screws, rotating massive wooden treadwheels to systematically pump millions of gallons of water out of the sealed workspace. Once the chamber was dry, teams quickly descended below the waterline to physically pack stiff, reactive mortar and heavy stone rubble into large wooden forms before the temporary clay seals yielded to the ocean. Mixing volcanic ash with hydrated lime and water triggered a chemical reaction, forming a highly stable calcium-aluminum silicate hydrate matrix. Modern Portland cement relies on a calcium silicate hydrate gel lacking long-term stability. The ancient mixture substituted aluminum into its atomic structure, providing exceptional internal cohesion. The Roman builders orchestrated localized geological events, manually packing stiff, reactive materials to forge a customized artificial rock. Modern material scientists long assumed that the visible white chunks in Roman walls were evidence of poor quality control. Excavations at an unfinished Pompeian construction site, frozen in time since 79 CE, proved otherwise. The site revealed that builders utilized a dangerous method called hot mixing. Instead of using a wet lime paste, laborers mixed dry, reactive quicklime directly with dry volcanic ash. Introducing water triggered an exothermic reaction, spiking the internal temperature of the mortar to nearly 200 degrees Celsius. This extreme heat prevented the complete dissolution of the lime, leaving behind brittle, porous, millimeter-scale calcium reserves embedded throughout the concrete matrix. These calcium reserves, known as lime clasts, are the engine of a terrestrial self-healing mechanism. When earthquakes or ground settling cause microscopic cracks to form, they naturally propagate through these brittle clasts. As ambient moisture infiltrates the fracture, it reacts directly with the calcium core. The dissolved calcium saturates the fluid and spontaneously recrystallizes into calcite, sealing the void before the fracture can spread. On land, the concrete heals its own wounds. But in the ocean, it executes a completely different chemical survival strategy. While saltwater aggressively degrades modern seawalls, Roman marine breakwaters use the corrosive ocean as a chemical partner. As seawater percolates through the massive concrete blocks, it slowly dissolves the internal volcanic glass. In its place, it grows aluminous tobermorite, an exceptionally rare, resilient crystal that requires extreme heat to synthesize in modern labs, but forms naturally here at ambient ocean temperatures. Over millennia, the continuous growth of these interlocking mineral plates heavily densifies the internal pores, significantly increasing the material's stiffness. This allows the breakwater to absorb the violent kinetic energy of crashing waves without brittle fracture. These walls function as open chemical systems, actively regenerating their own internal structure every day they remain submerged. If ancient chemistry creates materials that outlast empires, the modern construction industry faces an obvious question. Why don't we immediately replace our industrial cement with the Roman recipe? The search for alternatives is urgent. Global Portland cement production is an environmental behemoth, responsible for roughly 8% of all greenhouse gas emissions. This chart shows the initial carbon footprint of both materials based on a 2025 life cycle assessment. Producing Roman quicklime still requires calcining limestone in kilns at nearly 900 degrees Celsius, off-gassing nearly identical volumes of carbon dioxide per cubic meter as modern formulations. The Roman recipe is not a low-carbon miracle at the factory gate. Its true environmental value is realized only when measured across the structure's entire operational lifespan. Demolishing, disposing of, and completely rebuilding a concrete highway overpass every 50 years generates a catastrophic cycle of compounding emissions. If a self-healing structure survives for 5 centuries with minimal maintenance, that cyclical carbon debt is completely erased. Modern researchers are now racing to hybridize these timelines. Engineers are prototyping next-generation concretes injected with dormant bacterial spores and calcium lactate. When water enters a crack, the bacteria wake, consume the food, and excrete calcite, biologically mimicking the Roman hot-mixed clasts. For coastal defense, researchers are utilizing synthetic zeolites to design marine structures that intentionally allow seawater percolation. Instead of fighting the ocean, these seawalls will act as artificial reefs, growing stronger under chemical assault to protect coastal cities from rising climate threats. True sustainability requires abandoning the cycle of planned obsolescence. It means returning to an engineering philosophy measuring success not in fiscal quarters, but in permanence.